All right, so we just finished up looking at polynomial functions and their zeros, and now we're going to look at rational functions and their graphs as well. So remember that when we talk about rational functions, when we did our adding, subtracting, multiplying, simplifying, we always had to state the excluded values. Well, now when we're looking at a function, those excluded values are really important because they're going to tell us what the domain of our function is. Remember that since we can't divide by 0, we're going to have to restrict the domain when we have a rational function. So anywhere that the denominator would equal 0 is going to be a problem. So here, x minus 5, x cannot equal positive 5 because that would make the denominator 0. So that means that the domain of this function is going to be everything from negative infinity up to positive 5, but we don't include 5. Union positive 5 starting but not including positive 5 up to positive infinity. For number 2, we have x squared minus 25. Well, to solve that equation, let's give it a quick little factor, and we see that we have x plus 5, x minus 5. So what can x not be? X can't be negative 5 or positive 5, but the domain is not what do we not want. The domain is always what can we have. So we need to list it out, starting from negative infinity, and we can go up to negative 5. Then we have to skip over negative 5. We can go from negative 5 to 5, but then we have to skip over 5. And after that, we're good until we get to infinity. Okay, last one, x squared plus 25. If we look at where that equals 0, it's not. The only solutions that equation would have would be imaginary solutions, and those don't live on the graph, remember? So there's nothing that would make that denominator equal to 0, so all x's are fine. So the domain here is going to be negative infinity to positive infinity. All right, so rational functions are always weird. They have all sorts of things that can go wrong because of those numbers that have to be excluded from the domain. So the first thing that can go wrong with your domain is that you have a vertical asymptote, okay? So we've seen this arrow notation before when we talk about going towards infinity, what happens, but these first two are new. These you see in calculus a whole lot. This says, as x approaches a from the right. So what that little plus says is we want to approach a from the side greater than a. And then the minus means that I want x to approach a from the left or from below a. That's what that would mean. So if we look at this graph here, we're assuming in this case that there is a vertical asymptote right here. We know a little bit about asymptotes from Algebra 2. The graph is going to approach the asymptote, but it's never going to get there because that value does not exist in the domain. So look at what this says. As x approaches 0 from the left. So 0's right here. We're approaching 0, but we're coming up from the left-hand side. As I approach 0 from the left, what's my function doing? It's approaching positive infinity on the y. So that's how you can read that, okay? So what is a vertical asymptote and how do we find it? A vertical asymptote of the graph of the function is where the graph increases or decreases without bound as you approach the asymptote. So again, it's that idea of you're going to get real close to it, but you can't ever get there. You're always chasing that arrow, and you're just going to get closer and closer and closer, but you're never actually going to get there. So how do we find a vertical asymptote if we have the equation? This is the important part, okay? If f of x is some rational function of the form p of x over q of x, where P and Q have no common factors. What does that mean if they have no common factors? That means that f of x is simplified. This is why we practice that, okay? It has to be simplified, so anything that we can divide out, we need to do that. Then anywhere where the denominator would be 0 in the simplified form is going to give you a vertical asymptote. Now, a vertical asymptote is an equation, and vertical lines take the form of x equals some number. If you remember, just like we've talked about over and over again, no number on a graph can ever be naked, is what we like to call it. It has to have a label. It's either an X or a Y. So you can't just say 2 when you're talking about a graph. It's either X equals 2 or Y equals 2 or f of X equals 2. It has to have some sort of a label. So how do we find vertical asymptotes? Well, first we go and we try to simplify these. So this first function, number 4, f of X, let's factor the denominator. We get X plus 1 and X minus 1. There's nothing there that we can cancel out, so we just then look at the denominator and see where it would equal 0. There are vertical asymptotes. There's 2 of them. X equals -1 and X equals +1. It would not be okay to write plus or minus 1 in this context because this isn't actually talking about a number, it's talking about an equation of a line. So you should have 2 separate equations. Okay, number 5, very similar. When we factor this, we get x minus 1 over x plus 1, x minus 1. Well, the x minus 1's divide out. So what we have left is 1 over x plus 1. So this one only has one vertical asymptote at x equals -1. Something else happens where that factor cancels out. And then the last one, this is already simplified because x squared plus 1 doesn't factor. So that means there's no vertical asymptotes because this equation is never going to equal 0, kind of like we saw on number 3 up above. Okay, so asymptotes come from factors in the denominator after you have simplified. That's where you get vertical asymptotes. And that's important because we're going to look at both vertical and horizontal. Okay, so when that factor cancels out, what happens? That causes a hole in the graph. And you have to be really careful because the graphing calculator does not show that there's a hole. It will look like it goes all the way through. But what is really happening on the graph in that case is that the graph is doing something like this and it skips a point, okay? We don't have that entire vertical asymptote, but it has to jump over that point. So if you think about the one that we just did, where we had x minus 1 over x plus 1, x minus 1, and these canceled out. Well, that x plus 1 told us there's a vertical asymptote at x equals -1, but this one has a hole at x equals +1. So that's what we know when the factors divide out. So in calculus, we talk a lot about the continuity of a function. Where is it continuous and where is it not? And there's 2 types of continuity. You can have, discontinuity, where it's not continuous. You can have a removable discontinuity, which is a hole, and it's easy to remember because you can remove those factors. Or you can have a non-removable discontinuity, and that's when you have an asymptote. A hole you could fix by filling in one single point, but an asymptote you can't fix. You'd have to change the whole function. So that's how we find vertical asymptotes. The next thing that can happen is a horizontal asymptote for a function, okay? Now, here's what's weird about horizontal asymptotes, and this is why it's important that you pay attention whether it's horizontal or vertical. You can cross a horizontal asymptote. You can't cross a vertical one because it has to do with the domain, but a horizontal asymptote has to do with end behavior. So when we looked at polynomials, we really only had 2 options for end behavior. It either went up or it went down. With rationals, we have more options than that. With rational functions, it could go up, it could go down, or it could level out and go perfectly horizontal to the right or perfectly horizontal to the left. That's what a horizontal asymptote does. So that's why along the middle, you can cross it back and forth as many times as you want, as long as it eventually levels out and follows the asymptote. Okay, because it's really telling us what happens at the ends of the function, not what happens in the middle. Okay, now, how do we find a horizontal asymptote? This is a little bit woollier than the vertical asymptotes. So if you're a rule memorizer, then you can memorize these rules 1, 2, and 3. Put them on a flashcard. But you know how I am. I'd rather understand what's happening and be able to figure it out myself. So when you have two polynomials, one on top, one on the bottom, that's what makes it irrational. You're going to compare the degree of the numerator to the degree of the denominator. And here's the rules. If the degree of the numerator n is less than the denominator m, then the x-axis is going to be your horizontal asymptote. If the degrees are equal, it's going to be the ratio of the leading coefficients. And if the reverse is true, if the numerator's degree is greater than the denominator's, then the graph will have no horizontal asymptotes. Well, here's what I want you to look at on the following pages. And since we're not in class, I'm not going to make you work through all of these on your own, which is unfortunate because I think it's valuable. But I don't think that's going to translate quite as well in this video here. But here is the idea. If we look at what is happening as we approach positive or negative infinity. So we can use the table function in our calculator to plug in those values if we want. But if we go through this, here's what you should observe. The ultimate thing is here, okay? The question is your function top heavy or bottom heavy? Which of the functions is more powerful, okay? If the top of the fraction is more powerful, then the value of that fraction is just going to keep getting bigger and bigger and bigger, which means there's no horizontal asymptote because your arrows are either going to go up forever or down forever. Bigger, bigger, bigger in the positive direction, smaller, smaller, smaller in the negative direction. If the bottom of the fraction is more powerful, then the value will approach 0. Let's just think about like 1 over x squared, for example. Okay, the top is a constant, so the bottom here is definitely more powerful. If I start plugging in numbers, 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, the bigger the denominator of the fraction, the smaller its value becomes. So we eventually get out to like 1 over 10 squared, 1 over 100 squared. That's 1 over 10,000. These numbers are getting very, very teeny tiny. So if the bottom of your fraction is bigger, it's going to drag the value towards 0. And if they are equally powerful, if you think about if you had something like 4x squared over 6x squared, well, the power of these are going to cancel each other out. So you'd have 4 over 6, you're just going to be left over with 2/3. That's where your horizontal asymptote will be. So again, the question is, compare the power, as in like the strength, but also looking at literally the exponent, the power. If the top is stronger, then it just keeps getting bigger. If the bottom is stronger, the number keeps getting smaller until it gets really close to 0. If they're equal, they undo each other's power and you're just left with the leading coefficients. So let's look at these examples. Number 7, I'm going to compare. This is an x squared. This is an x squared. We don't care about the rest of it. We're only looking at the leading term and the leading term. That +1 is not going to affect where the asymptote goes. It's just those first two terms. So when I look at that here, these are equal in power. So their powers cancel each other out. And so our horizontal asymptote is y equals 9/3, which is 3. Horizontal lines start with y equals. You may have learned in Algebra 1 the acronym HOY, VUX. HOY, horizontal, zero slope, y equation. VUX, vertical, undefined slope, x equation. So that'll help you remember. Vertical asymptotes start with x equals. Horizontal asymptotes start with y equals. Okay, so if we look at number 8, same thing. We just want to compare the first term and the first term. The question is, which one is more powerful? Well, a squared is more powerful than a first power. So this is getting bigger faster, which means the bottom getting bigger actually makes the fraction smaller. So we're going to drag down to 0. So the vertical asymptote there is y equals 0. The last one, if we look here, 9x cubed compared to 3x squared, well, here the top is the one that has all the power. That means our number is just getting bigger and bigger and bigger, which means the value of this fraction is going towards infinity. We don't care that it's infinity or negative infinity. All we know here is that there's going to be no horizontal asymptote because it never flattens out. It either keeps going up forever or it keeps going down forever. That's like our typical end behavior. So that's really what I want you to practice today is your vertical asymptotes, your domain, your horizontal asymptotes. When I see you next time, we'll work on actually putting these on the graph.